Think back to the cartoons you grew up watching. Somewhere in almost every one of them, a cat gets thrown, dropped, or knocked off something impossibly high. And no matter how it happened, it always twists around midair and lands perfectly on its feet, like nothing happened at all. It became one of those quiet and chilled facts nobody ever questioned. The kind of thing you just absorb without ever really thinking about it. Cats land on their feet, everyone knows that, but somewhere between the cartoons and growing up, almost nobody ever stopped to ask, is that actually true? Not true enough for a cartoon, actually, scientifically, verifiably true. You drop a cat from a height with absolutely zero spin, no rotation at all. By every rule of physics you learn in school, it should land however it starts, sideways or upside down. Instead, it lands on its feet almost every single time. For over a century, this was a real, documented problem that actual physicists could not explain. The normal name for it is the falling cat problem, and it's not a nickname invented for a video. It's the actual term used in physics papers going back over 100 years, written by serious scientists stuck on a question that sounds almost too simple to be real. How does a cat with nothing to push against turn itself around in midair? To understand why this became a genuine scientific puzzle, start with a basic law of physics called conservation of angular momentum. In plain terms, an object in the air with nothing touching it cannot start spinning from a dead stop with no outside force acting on it. A figure skating can speed up an existing spin by pulling their arms in, but they can't create a spin from nothing. That's the rule. And the falling cat appears to break it. Drop a cat with zero initial rotation and it still flips itself over before it hits the ground. No wall to push off, no ledge to kick against, just empty air. The first person to seriously study this wasn't a physicist, he was a French scientist named Étienne-Jules Marey, and in 1894 he pointed an early high-speed camera fast enough to freeze motion invisible to the naked eye at falling cat. What Marey captured was a strip of black and white photographs showing, frame by frame, a cat drop upside down, rotating itself completely around before landing on its feet. Every single time. It became some of the earliest scientific proof this wasn't a myth. Cats really were doing something that looked on paper physically impossible. For decades after, physicists genuinely argued about the mechanism. One popular early theory was that cats use their tails like a helicopter rotor to spin themselves around. It doesn't hold up. Cats with short tails, and even the tailless Manx breed, performed the exact same twisting maneuver with the same success rate. Whatever was happening, it didn't depend on a tail. The real answer came down to something a cat's spine can do that a rigid object can't: bend independently at the middle. A falling cat doesn't rotate its whole body as one single unit. It bends at the waist and turns its front half and back half in opposite directions, almost simultaneously, because it tucks in the legs on one half while extending the legs on the other half during each partial turn. Each half of its body has a different resistance to rotating. Call it moment of inertia. By alternating which half is tucked and which is extended, the cat can rotate its front end further than its back end cancels out. Then reverse the setup and do the same thing again for the back half. Add both partial rotations together and the cat ends up facing the ground, having never violated conservation of angular momentum at any single instant. The total spin of the whole body added together always stays at zero. It just distributes that zero cleverly enough to end upright side up. Here is where the hypothetical gets interesting. That entire mechanism depends only on the cat's own flexibility and the physics of rotation, not on gravity itself. Gravity determines how fast the cat falls and how much time it has to complete the maneuver. It doesn't determine whether the maneuver works. So if you dropped a cat somewhere with a fraction of Earth's gravity, on the moon for example, the physics says the twisting reflex would work exactly the same way. The cat would still turn itself right side up using the same mid-body twist. The only real difference is time. With the moon's gravity at about 1/6 of Earth's, The fall would happen roughly 6 times slower, giving cat far more time to complete the same rotation, and likely an even gentler landing once it got there. So how about Jupiter? Jupiter doesn't even have a solid surface to land on, it's a giant ball of gas, but it does have gravity roughly 2.5 times stronger than Earth's. Imagine, purely hypothetically, a cat falling through Jupiter's upper atmosphere. The twisting reflex itself would still work exactly the same way, because the spin bending mechanism doesn't care how strong gravity is. What changes is the timing. With gravity pulling that much harder, the cat would accelerate downward far faster than on Earth, leaving dramatically less time to complete the same twist before reaching a higher speed. The maneuver isn't instant, it takes a fraction of a second to execute. It's a small slice of a long slow fall. On a world with stronger gravity, that same fraction of a second has to work against a much steeper drop. The physics of the twist doesn't fail. The margin for error just gets a lot smaller. Picture two cats falling together, wrapped tightly around each other in a hug, spine pressed against spine, held together as one rigid unit for the entire fall. Individually, each cat has everything it needs to twist itself upright. Together, locked in that embrace, neither one can. The moment two flexible spines are forced to move as a single rigid block, the entire mechanism, the maneuver depends on disappears. It isn't that the physics stop working, it's that the one tool the physics actually needs, a spine that can bend independently at the waist, has been taken away from both of them at once. Conservation of angular momentum doesn't care about mass, two cats together weigh more than one, and that alone doesn't break anything. What breaks it rigidity. The moment nothing in the system can bend on its own, the whole tree collapses not because a law of physics failed, but because the physics never had the flexibility it needed to work within in the first place. This is exactly why NASA cared about a question that started out sounding almost silly. Physicists studying the falling cat problem in the 20th century weren't just satisfying curiosity. The same mechanics, a body reorienting itself in midair using nothing but its own limb movements, turned out to be directly useful for understanding how astronauts and satellites could control their orientation in zero gravity, where there is nothing to push against and no atmosphere to help. Some of the physics used in a real spacecraft attitude control was informed by the exact same equations first worked out to explain a falling cat. None of it started as a serious research question, it started as a genuine, almost absurd argument in the late 1800s about something everyone had seen but nobody could actually explain. And it turned out the explanation was hiding somewhere none of the early theories thought to look, not in the tail, not in the air, but in the simple, flexible bend of a cat's own spine.